Hey, ladies and gentlemen, welcome back. Um, Happy Monday. Here we are, another week and another class here. So, as you can see, I'm not with you. I hope you had a great weekend and are doing well today. Today, we are going to continue to look at the last little piece I want us to be responsible for this unit, and that's going to look at more application questions, maximizing, minimizing, but max and mins on an open interval type question. So very similar. But before we get rolling, here's the question. I want us to real fast take a moment and ponder and reflect here. Two questions to ask yourself here. So number one, on this Monday here, as we wrap things up, where are you now in your quest to understand these application max and min problems? So where are you at now? And then again, as we've talked about here later this week, where do you need to be, or what do you need to do between now and our test to be ready to go here? So I know these application questions get harder. They're tougher. They're not simple. And now here I am not with you to help you out with it a little bit. But maybe you're good. Maybe you're keeping up with stuff and this makes sense and you can work through these. Great. Maybe some of us were struggling through some of this. What do you need to do between now and, in this case, Thursday to be ready for a test? So what's your plan? So don't just wait till the night before the test and be like, well, I don't know what I'm doing. I got to figure this out. Start working now. Use the people around you. Use myself. I'll be back. I'll be, more than anything, love to help you. So um, let's make this a great week and let's understand some pieces and things. Now, the last 3 days, we've been working on these application questions. These answers are in Canvas, and I'm kind of going to jump here to the second half here a little bit to what you were working on last week. Right now, again, you're going to have some time in a few moments here to maybe work some more on this. These questions aren't due until Tuesday until tomorrow. So, but have your neighbors, if they understand how to do these, how to get to a place, not just copy things down, obviously, but have them help you set them up, get some help with it. And we'll do that later on. But again, answers are in Canvas, as you see here. A lot of you are getting these answers in class on Friday and Thursday, which is good. But here's where I want us to go today. I don't have notes for you today, so I need us to copy some things down. But I want you to at least see two examples of different problems. But these are going to be application questions, but the difference now, they're going to be on an open interval. And that's going to, how I handle the proof of this is going to be a little bit different than if they were on a closed interval. And so it's going to be important for you to see the difference and a little bit of the setup and especially the proof part of this and what I would expect. But the hard part here is recognizing an open interval versus a closed interval. And so I need us to dial in. And again, this is harder because I'm not even with you. I'm talking to myself right now. This is going to be hard for me to do. So there's two problems again. And sub, if you would pause the video as needed. If they need more time to write things down, please do so. But if everyone would pull out their notes, though, there's two examples I want us to look at. Here's the first one. And this is, I showed you this before we started this unit. I have this cylindrical can right here. So it's a close can, so it has a lid on it, it has a top and a bottom. And I need my can, my cylinder, to hold 1 liter, or what we're going to use here in a moment is we're going to think of this in terms of cubic centimeters. It's going to hold 1,000 cubic centimeters. So because it's cubic centimeters, that's my volume. What I'm asking, though, is we want to minimize the amount of material needed for this can. So maybe I'm working for Campbell's Soup, and I want to have a can of soup that holds 1 liter of soup, but I want to have the least amount of material, tin, to go around the outside of this to save my company money. What's the least amount of surface area that I would need for this? So jot it down. Let's talk our way through this and see where we get to. So like closed intervals, the process is going to be the same. Number one here, I want to ask myself, what is it I'm trying to max or minimize? Well, I'm trying to minimize what? Well, minimize the material needed for the can. Well, that's really like saying I want to minimize my surface area. So I need to come up with an equation for surface area. I'm going to call it SA for surface area. Now, how many of us remember how to find the surface area of a cylinder? And again, if you were here in front of me, I would be demonstrating all this. So you're going to have to envision me holding up a little cylinder right now. You see it right here. But what surfaces do we have? Well, when I have a cylinder or any 3D object, in this case, I have a base on this, right, the bottom of this thing. And I also have a top. These two things are the same. So I have two of these base areas, right, top and bottom. So I have two of these bases. But then I also have, the other piece of this is I also have what we call in geometry our lateral face. So I have the side of this thing. So what the side of this actually looks like here is I look at the side. So let's break these apart. First one's not bad. How do I find the area of the base? Well, I have two of them, so I have 2 times something, but what shape is the base? Well, the base of this is just a circle. A circle is area of a circle, pi r squared. So you're going to have 2 pi r squared, right? So I have a circle on top, I have a circle on the bottom. Sometimes you see this drawn in geometry like this, so I have that. But then my lateral face is actually, if you unfold if you unfold your cylinder, if you were to cut it and unfold the outside of it, it actually looks like this, where it's just a rectangle. Right? And again, if I wish I was here, because I would demonstrate, envision me having a piece of paper rolled up in terms of a cylinder, and if you open it up, it's just a flat piece of paper. It's just a rectangle where this thing has a base and a height. So this lateral face right here really is just some base times height of this rectangle. It's just what's the base of this rectangle? What's the height of this rectangle? Well, the height of it is the height of the cylinder. So that part's not a big deal. That's just the height. It's just, how do I find the base of this? Well, the base of this is rolled up here. The base ends up being, and some of you are maybe thinking this, maybe you're saying it, the base is actually the circumference, 2 pi r. It's the distance around the outside of my circle. So if I roll that up, it's going to go all the way around my circle. That's 2 pi r. So the equation for this is then, at the end of the day, and maybe you still remember this from geometry, I'm going to have the base, which is 2 pi r, but then times the height, so times h. So my surface area for my cylinder that I want to minimize the surface area of, it's going to be 2 pi r squared, because I have 2 circles, plus 2 pi r h. You're going to see questions in a moment on the homework today, tomorrow, whenever you get to these with cylinders like this. Some of these talk about not being a closed cylinder, but they talk about being an open cylinder. It just means you don't have a top on it. So it's like you don't have one of these on there. So the only thing that changes then is I don't have one of my bases. I only have one circle. I don't have a top on it. So be aware if you have a top or a bottom on it. This one has a top, it's closed. And so I have 2 circles here for my surfaces with it. Now, this is like what we've been doing, Mr. Roy. We've been doing the same thing. We have an equation. My equation now, I have r and h's in it. So again, the goal is, can I write this as one variable? Well, what's the one constraint about my cans that I'm making for Campbell's soup? The one constraint is what? How much volume does each can have? They want me to make this so it has a volume of 1,000 cubic centimeters. Not more, not less, but exactly 1,000 cubic centimeters. What's the equation for volume of a cylinder? Oh, we're just going to go silent, huh? So no, the volume of a cylinder is actually pi r squared times h is what the volume of my cylinder is. So that's what volume is pi r squared h. If I set that equal to 1,000, now we can solve for h or r. And now here's where I would be wise about which one I want to pick. I want to make this as easy as possible. And so as I look at this, it's probably going to be easier to try to solve for h. And as I look over here to my surface area equation, I probably want to solve for h here as well, because I only have to plug it in once. If I solve for r, I'd be plugging it in twice, r squared and r. And so I want to maybe solve for h because I think it's going to be simpler. So what is h equal based upon this constraint? Well, h is going to be 1,000 divided by pi r squared. And so like what we've been doing in the past, I take this constraint, solve for one of my variables, I plug it into my equation that I want to minimize or maximize, and now I'm just writing this as one variable, in this case all in terms of r. So I'm going to have 2 pi r squared plus 2 pi r, but then now h is this thing, 1,000 divided by pi r squared. That's my equation now, all in terms of one variable. Again, if we need to pause. I sometimes get too excited, go a little too fast, so forgive me. I might clean this up a little bit more. So when I say clean it up here, I'm looking at this side over here where I have a pi on top, I have a pi on the bottom. I could cancel that out. I might clean this up. I have an r on the top right here. I have 2 r's on the bottom, r squared, so I might take one of those out. 2 times 1,000, that's going to be 2,000. So if I rewrote this, my surface area equation is going to be 2 pi r squared plus, I'm going to have 2,000 over r, since I just have 1 r left. Now, because I'm going to derive this in a moment, I might just make this a little bit nicer yet to derive. I actually might put this r that's on the bottom. Is it okay if I write this and write it as r to the negative 1? Put it on top? But now, you feel like you could derive this. So what's the derivative of my surface area? Well, if I derive this first piece, bring the 2 down front, so now I have 4 pi r to the first, plus, bring the negative 1 down, so I guess that's going to not be plus, but it's going to be minus 2,000 r to the negative second power. If I set this equal to 0, keep cooking here, I'm going to have 4 pi r minus 2,000, and I might write it like this, over r squared. And this is kind of like, the math now is kind of like some of those harder questions the other day. I might not get a common denominator if I'm doing this and worry about my critical points that are non-differentiating, those CP and Ds. I might just move this to the other side. So I might add 2,000 over r squared to this side, but then add 2,000 over r squared to that side. So what I actually really have now, I'm going to have 2,000 over r squared equals 4 pi r squared. Then maybe I multiply by r squared, multiply by r squared. So now these cancel out. So I have 2,000. Some of you are already done with this, but I have 4 pi r cubed. I feel like I had messed something up here. Here's what I messed up. Why don't someone say something? It's right. This is r to the first here. So I really have that times now be r cubed right here. Since I have r to the first, r squared. Sorry. Solving for r, what am I going to do? I'm going to divide by 4. I'm going to divide by pi. So I'm going to divide this by 4, divide this by pi. So maybe I write this. What is r cubed? R cubed is going to be 2,000 divided by 4 is 500. So I actually have 500 over pi. That's some number. I don't know what number that is without a calculator. But then I'm going to take the, not square root, but cube root of both sides. So what is r? My critical point is what I'm finding here. What's my critical point? R is the cube root of 500 over pi. Or if I look at my notes here, if you type that in your calculator, that should be, or if I grab a calculator, I think that's roughly, again, decimal-wise, just to give you a reference here, that's roughly 5.4 is what I'm getting here for r. Does that look right? The cube root of 500 over pi? And again, that's my critical point. Now, this for the most part, I know it's a different kind of question. We haven't done a cylinder like this, surface area like this, but now the question I'm going to ask us is this though. What kind of interval do I have? Well, my variable that I was using through all this is r, so I'm thinking of r here. Maybe I'll do this for visual sake here. Let's bring this thing down. Let's just see my cylinder, and this is where I wish I was here so I could kind of demonstrate for you a little bit. But the radius of my cylinder, again, this is the radius here. This thing has a height to it. What's the interval for my radius? Well, my radius could be, think about the radius could be 0, right? It could get anything bigger than 0. Again, the smaller my radius gets, my height's going to get bigger and bigger and bigger. It's going to be like a big, huge pixie stick. Here's what it's going to be if the radius gets really, really small. Can I have a radius of 0? Well, technically, no, but anything bigger than 0 would mean I just have this little long straw-looking cylindrical shape. It's going to be super long if it's going to hold 1,000 cubic centimeters of volume. But now, how big can R be? Now, this is where, again, take this cylinder that I've drawn on the side here. Imagine me now taking my hands on this cylinder. Well, if R is going to get bigger, what has to get smaller? H has to get smaller. This has to come in. This has to come in. So think about taking this thing and flattening this cylinder out. But as I do so, all of a sudden now my radius has to go outward. My radius has to get bigger and bigger and bigger outward. So as I smash this down, the height becomes smaller. My radius is going to get bigger and bigger and bigger and bigger. The more I smash this thing down, because it has to have this much volume, it has to have 1 liter, 1,000 cubic centimeters. Where does all that volume have to go? It has to go squirting out on the sides here. And the more I smash it, H goes to 0, R is actually going to go forever, which is hard to think of. But this thing is going to become this flat pancake that's going to be huge. And how huge? It's going to actually be infinitely, this is going to be infinitely long here. So my radius has to be something bigger than 0, but if I make H smaller and smaller, it's going to be infinite in length. Does that make sense? And now this is not a closed interval. This is what we refer to as an open interval. And that's why, again, this is entitled open intervals. This is not bounded by my constraints to be from 0 to some number. There's no bounds on it, what it might be. Now, part of this comes from this equation right here. I wish you were here. I wish I was here with you so you didn't have to watch a video to see all this stuff. But as I scroll this down here to see both of this, part of it comes from this equation right here. If you want to think of this is my constraint right here. Pi r squared times h. As h goes to 0, that means this has to get bigger and bigger and bigger for this to equal 1,000 is kind of what we're saying. It's not like all our other equations we did last week where you had something plus something else equal this, and as one went to 0, the other one equaled some number. As this gets small, as this goes to 0, this has to get bigger and bigger and bigger for this still to equal 1,000. And that's what we're saying here. How big does that have to be? It has to be, it's going to go to infinity. So here's what's different. I recognize it's an open interval. Great. Some of us are still thinking, does that make sense, Mr. Roy? But now the proof in the pudding is now different. The proof in the pudding is this. How do I prove this now that this critical point, the critical point that I got right here, r equals the cube root of 500 over pi, or 5.4, what I'm going to have to do now is I can't make a table because I can't have infinity on a table because infinity is not a number. It's a concept. So instead, we called it the first derivative test last week or the week before that. I'm going to use a sign chart to show this. But it's a sign chart for the first derivative. So again, my first derivative in this case was my surface area here, right? So this is my first derivative, what it is. I'm using this critical point. And if you want to, if this is easier, sure, just use 5.4 if you want to, or that's the cube root of 500 over pi. But if I plug something less than 5.4 into my derivative, is it positive or negative? Again, we're looking at the derivative here because it's a sign chart for the derivative. And technically, if I should be technical here, technically this does not go from negative infinity over. This starts at 0, right? That's what my interval says, 0, but it goes forever to the right. So if you plug something between 0 and 5.4 into the derivative, like let's say we plug 1 in, what is 2 times pi times 1? Well, that's going to be 2 pi. And then plus, this is going to be 2,000 over 1, or just 2,000. This is going to be a positive number, so I have a positive right here. If you plug something bigger than 5.4 in, like 100, you're going to have a huge number here, but then you're going to get a, actually, Mr. Roy, this is where I wish I was here. How about, Mr. Roy, you plugged into the right thing. How about the surface area here? So let's go back here. If I plug 1 into the surface area, what's 4 times pi times 1? That's going to be like 4 pi, sorry, over 2,000 over 1 squared, which is still 1. This is actually not going to be positive. It's going to be negative. And again, so using either this, or again, you could use this version of it right here, but I'm going to get a negative when I do that into the derivative. Sorry, I plugged in the wrong one. Forgive me. If I plug something bigger than 5.4 into the same equation, like 100, 4 times pi times 100, that's 400 pi, but then minus 200 or 2,000 over 100 squared, that's going to be minus a fraction. You're going to have a big number minus a really small number. You're going to get a positive here. What does that tell me about my function, about the surface area? That tells me that my function was going down. Now it's going back up. So that this point right here has to be a what? It has to be a minimum. And so if I want to minimize my surface area, the radius needs to be roughly 5.4, or the cube root of 500 over pi. But this is the proof, though. I'm using a sign chart for my proof now to show that if it's an open interval, because I can't make a table. Now the last question is this then. If that's my answer, I go back to the problem. They say, what are the dimensions to minimize all this? So if I go back down here and just write my sentence then, well, I know what R is. How would I find H? And again, you guys are looking at this board like, what just happened here? Like a bomb went off on here. But this is where I find H right here. H is 1,000 over pi r squared. So if I know that, if H is, what did I just say, 1,000 over pi r squared is what H is, and I know R is this, I would be okay with you writing it like this. I have 1,000 over pi, but then it's R squared. What is R? R is the cube root of 500 over pi. I'd be okay with you writing your H like this and leaving it like that. That's the exact answer. If, again, not worrying about simplifying this, what it might be. If you type this in your calculator, again, I have to take R and square it, take it times pi, and have 1,000 divided by this. I believe H comes out to be roughly, good question here, Mr. Roy. H comes out to be roughly 5.4 squared times pi, typing it in right now, 1,000 divided by all that. This is roughly like 10.9. But I wouldn't have to find my other dimension, and that's going to be H here. But this would be okay. So if I want to write this to minimize the surface area, the dimensions need to be, well, my radius, again, if I wrote it exact, is going to be the cube root of 500 over pi centimeters. Then my height is going to end up being, again, and I'd be okay with this, writing it as 1,000 over pi times my radius squared, so pi times the cube root of 500 over pi centimeters. And that'd be a sentence. But those would be my dimensions. Again, this is roughly 5.4 centimeters. H was roughly 10.9 centimeters. But those are going to be my dimensions to minimize my surface area to have exactly 1 liter of volume. Overall, it's the same process. Again, the proof, though, is different because I have to make a sign chart. can I share one more with you? One more, and then I'm going to be done. You want to listen to the rest of this chapter here, but here's the last little piece I want you to see. A similar question. I don't know if you remember when we started all this stuff. The first question I had for you was, we're making this rectangular pin for our goats or whatever we had in there, and we wanted to minimize our, I think it was maximize our area is what the question was. This is kind of a similar question, but kind of reversed a little bit. So I wish to fence this rectangular pasture, but I want to have exactly 300,000 square feet of pasture inside this rectangle. But now one of the sides I share with my neighbor. So my neighbor shares a side. Now the neighbor said he or she agreed to pay for half of the cost of the fencing that touches their side. What dimensions do I need to make this rectangle to minimize my cost? Again, and I probably want to make something, again, but it has to have 30,000 square feet. But I want to make something that more of it's probably on my neighbor's lot line since they're paying half of it if I want to minimize my cost. But what do these dimensions have to be? So I might draw a little picture. I got a picture here. Again, the neighbor side is going to be different. Now, what I don't know here, they don't tell me what is the cost. It's not like, oh, it costs this much for this side and costs that much for that side. All I know is the side the neighbor is half of the cost. So if I think of this is kind of like if I think of this as this side is X right here, maybe I think of this side as Y right here. I could do that. I got to pay for X. I got to pay for Y. Actually, I got to pay for Y over here too because that's not the neighbor's. But what about the neighbor's side here? Well, if this is cost is X, whatever X might be, the neighbor's side is going to be one half of X. Does that make sense? And so as I look at it again, what am I trying to minimize? Well, I'm trying to minimize the cost. If I start writing an equation, the equation for cost really is, this is going to be actually, I have to pay for the cost of this side, pay for the cost of that side, this side, I have to pay for half of it on that side. It's really a perimeter formula is what the cost is. I'm going to have to pay the cost for X plus Y plus another Y plus half of X. It's really just saying I have to pay for two Y's, but then I'm going to pay for, if I have 1X plus 1/2 X, I'm paying for 1.5 X. I'll write it like this. But that's going to be the equation that I have. It's a perimeter equation. Now what's different though is what's my constraint here? What's the one thing that has to be true about my rectangle? It has to have 30,000 square feet here. So my area has to be 30,000. Well, if I look at my picture here, I also know that area in this picture, because it's a rectangle, is going to be X times Y. Because that's my rectangle. I have X by Y for my dimensions. So we need to solve for X or Y from the area and plug it back into my cost over here. So it's the same thing we've been doing, except for kind of backwards here. So let's, I don't know which one you want to solve for here. So if I solve for, that really doesn't matter. I'm going to solve for Y. If I solve for Y, this is going to be what? Divided by X, I'll have 30,000 divided by X. What am I doing? I'm going to plug that in for Y right here. So what's my new cost equation? It's going to be 2 times 30,000 over X, but then plus 3 over 2X. But now I just wrote this all in terms of the same variable, wrote it in terms of X. Again, maybe I do a little cleanup here and clean this up. This is really going to be 60,000 over X. I might write it like this, put X to the -1 because I want to derive in a second. But now again, where do I find my max and mins? I find them at my critical points. Well, how do I find critical points? I have to derive. And so if I were to take this cost equation and derive it, so the derivative of my cost, I'm going to get negative 60,000 X to the -2 plus 3 over 2. Now again, what am I doing with this? Setting this equal to 0. So if I set this equal to 0, Again, this is negative 60,000 over x squared plus 3 over 2. And again, I would not get common denominators. I would just move one of my fractions over. So I might add this piece over. So if I add that over, what I'm going to end up with is positive 60,000 over x squared equals 3 over 2. Then now I'm just simply cross multiplying. So if I do that, I'd have 2 times 60,000, 120,000. 3 times x squared, 3x squared. And as I solve this now it's simply divided by 3. So I'm going to get 120,000 divided by 3 would be 40,000. And then my last step, take the square root. And again, x can't be a negative number, so I just have the positive square root. But this comes out to actually be a nice number. The square root of 40,000 is going to be 200. So this is my critical point here of what it might be. Sure. Again, kind of the same process. It's just kind of flipped here of what it might be. Now, here's the $1 million question. All this work here, sorry, on the smartboard, I got to keep scrolling down. What kind of interval do I actually have going on here? So what is this interval? Well, my interval, we end up doing everything in terms of x. So if I'm thinking this in terms of x, so let's go back and look at my picture and look at this constraint right here. How small could x be? Well, if this is what I'm calling x right here, is this length right here, that's x. The smallest it could be is anything bigger than 0. X can't be a negative, so it has to be anything bigger than 0. Technically, it can't be 0, but anything bigger than it can be. Now, how big can x be? Well, based upon this constraint, you have to have this much area inside of this pasture. Like this pasture has to have 30,000 square feet, right? If x is going to get bigger, y has to get smaller. So if I make y smaller, right, if I squeeze this down, so pretend like I'm squeezing this down, but all this area is stuck inside of here, right? What's going to happen to x as I squeeze this down? X has to get bigger and bigger. But again, it's like taking something and I'm stepping on it. I'm making it as flat as a pancake. What's going to happen to x? It's going to go forever out. The more you squeeze y and make this tinier and tinier and tinier, it's going to make x go out farther and farther and farther. How far is it going to go out? Because all this area has to go somewhere. It's going to go out forever. The closer y gets to 0, x is going to get closer to infinity. And so this, again, makes this an open interval because it goes on forever. So what I would expect if I recognize it's an open interval, I can't make a table because infinity can't go on my table. So instead, I make a sign chart. And my sign chart's going to look like this. I'm starting at 0 and going forever, so 0 to forever. I'm using my critical point, which we just found to be 200, right? But what I'm using now, though, is I'm using the derivative. In this case, it's my cost here. That's the derivative right here. So this or this, right? This is made the same way to write it right here. So I'm using that one of those two pieces here. If I plug something between 0 and 200 into that, like 1, if you plug 1 into this, negative 60,000 over 1 squared, 1, plus 3 over 2, is that going to be positive or negative? Well, that's going to be negative, Mr. Roy. If I plug something bigger than 200 in, like a million, this thing is going to be huge. If I have this over something huge, that's going to be really, really small, plus 3 over 2, that's actually going to make it a positive number because this fraction is going to be so small there. And again, you could try this, use your calculator. Again, I'm not here to show you all this, but what's that tell me about my function? Well, that tells me my function was going down. Now it's going up. What happened at 200? Well, at 200 it had to be a low point. This has to be a relative minimum. And that's the proof that I want to see. I want you to always just show me that this is going to be my critical point is my max or my min. And the proof would be making the sign chart here. Now let's go back to the question was, what are the dimensions? Well, you just found x. X was 200. I need to also find what's the dimension of Y. Well, right here's where I find that again. So this is much like we had before. So Y is actually going to be 30,000 divided by 200. If I do that, it's 30,000 divided by 200. I believe Y is going to end up being 150. And now I can write my sentence. So what are the dimensions to minimize my cost? I can say something to this fashion: to minimize the cost, the dimensions need to be 200 feet by, right, feet, as we're dealing with feet here, yep, feet by 150 feet. Those are my dimensions. But now I can't just say this, though. I would on a test. I'd have to say more, though, again, because where do I want this 200 feet to be? I need that 200 feet to be where? That's my Y value, or my X value, sorry. I need the 200 feet to be the longer one. So maybe I need to say that where, maybe in parentheses, where the 200-foot side is shared with the neighbor. Again, I want my neighbor to have the bigger part of it if I want to minimize my cost here. But I need to maybe classify and say that. Until we do a few of these. Open intervals, again, recognizing they're open interval. That's always a little bit of a struggle, but you have to ask yourself, is it, as one dimension gets bigger, what happens to that, my dimension I want to find? Does it, how small does it get? Well, maybe probably goes to 0. But as the other dimension gets smaller, how big does my dimension that I want to find get? In this case, it goes to infinity of where it might be. Again, tomorrow, I'll be back tomorrow. Tomorrow is going to end up being kind of a work day and start reviewing through all this stuff for our test on Thursday. And so tomorrow I'll be here to answer questions. I know there's probably some questions that we might have here. Some of us, again, now the rest of the period, there's plenty for us to do. The sub is going to pass out a worksheet. This worksheet, I called it 3.7b. There's 9 questions on there. I'm going to ask us, can we try 7 of the 9? Again, and I'll even say this, can we do these, again, by, in this case for you, by Wednesday, so not even due tomorrow, right? So, because I understand some of us, we need to finish this right now. This is due tomorrow. And so some of us, again, maybe we need to get help from our neighbors and stuff and work through these questions. The answers are in Canvas, but again, I want to see proof. I want to see a sentence. I want to see that we can set up the equations to derive these and derive them correctly. But those are going to be due tomorrow. These other ones will take some time if we need more time tomorrow to work on these. So I need us, again, there's power in struggling. But again, don't struggle alone, though, right? Let's struggle with each other, right? Let's help each other out. We have some great minds in this classroom. Again, all of us, I think the world of and stuff, and we can do some great things, but we got to try these and figure out where are our issues, so we can get them figured out for our test on Thursday and get it ironed out. So good luck working. Again, answers for these 9 questions here. They're in Canvas as well, so they should look something like, like this. The answers look like this, so I have them in here. You're going to see some things where you have some cylinders again, like number 4 is a cylinder one. You have some other ones where they're rectangles, some things, some pieces here to do. So you pick which ones you want to look at and do, but the answers are there, and I left the solutions with the sub as well. So good luck. Help each other out. Have great attitudes, and I'll see you tomorrow. Thank you.